Okay, hello everyone. Welcome to our fifth workshop of the quarter for the Introduction to Competitive Programming series. And today we're going to cover binary search. Before we go to our workshop stage, we'll do the raffle. For those who don't know, every time we do a raffle based on the results, based on the number of submissions, correct submissions to the contest we have every week, and the winner of the raffle will get $20 Amazon gift card. So this time we only had 2 people. Let's see. Okay. Good job. Okay, nice. So next time, make sure to participate in our weekly contest. And the more correct solutions you submit, the more entries you get to the raffle. Okay. All right. So let's move on to our today's workshop. So today we're going to cover basics of binary search, what it is, how to run it, how to code it, and we'll do a couple of example problems to describe how it works on real-life examples. Okay, so before we actually start, let's imagine a real-life situation that can happen to any of us. So let's say that you decided to look into the future, and in a couple of years, you'll find yourself graduating from UCLA. However, you realize that there is a new policy in place that you cannot refund any money left over on green card accounts. So you decide to keep all the money to yourself and not let the school take the money. So you want to spend all the green card money you have before you graduate and get locked out of your account. Well, we all know that we can use our green card easy pay money at UCLA store. So let's say you went to the store and you just want to buy one item and you want to buy the most expensive thing, well, that you can afford at the UCLA store. And conveniently for you, they sorted all the items they have by the price. So let's say this is the variety of the items you can buy at the UCLA store, and you need to find out the most expensive thing that you can still afford with the funds you have. Well, this is some kind of a challenge, and there are different approaches to this problem. So let's consider one of those, linear search. Well, you decide to check every item one by one. You start from the cheapest item, the $2 one, and you go to the cashier and ask, can I buy it? They say, yeah, you can afford it. Well, if you can afford it, you move on to the next item, and you ask the cashier, can I afford this one, $10? Yes, I can afford it. And you continue doing that, checking every single item for $23, $40, $60, and then you get to the item that the cashier tells you that you cannot afford. You realize that you cannot afford $250 software. Well, what does that mean? That means you cannot afford anything that's more expensive than this software, including this software. And the most expensive item that you can still afford with the money you have is the headset for $60. So you buy that one. Okay, so let's quickly summarize what we just did. Well, we started from the first element, in our case, from the cheapest element, and notice that we had all the elements sorted. And we move on from, we repeatedly check every single element until we get to the element that we are looking for. In this case, we are looking for the element that, the first element that we cannot afford, meaning that the previous one was the highest value item that you can still afford. Okay, can anyone tell me what the time complexity of this algorithm is? Yes. So basically, you need to check every single item, and in the worst case, you need to check all the items. So your algorithm runs O of n. And while in many competitive programming problems, this is a very efficient algorithm, you know, O of n is one of the best you can get with n elements, and this is a polynomial time. So this algorithm is pretty good. However, I'm telling you that for this particular problem, there are more efficient ways to find the solution. And even with O of n, if there are 1,000 products at the UCLA store, you might have to do 1,000 checks, which is definitely not efficient. And there is a way to do it much faster. So looking at the process that we were, looking at the way that the items were laid out for you, there is some observation we can make. Notice that the items we have are sorted by their value. So by only one check, we can actually devise more information than just knowing if we can buy this item or not. So let's say we check the item for $60 and the cashier tells us that we can afford it. Well, that means, well, can anyone tell me what can we say about everything cheaper than the headset? If we can afford the headset.
We can afford all of them?
Yeah, so we can actually afford anything that's cheaper than that. So in our case, we don't need to check all those items at all because we want the most expensive thing. And if we know that the headset is currently the most expensive one, those cheaper than that are not in our interest. So right, we can afford everything that's cheaper than the headset. Well, let's consider the other case. What if the cashier tells us that we cannot afford the headset? Is there anything we can say about everything that's more expensive than that headset? Right. So another observation we make is that if we don't have $60, well, that's pretty obvious that we don't have $250 or $1,000 as well. And this allows us to eliminate all the items that go to the right of the headset that are more expensive than the headset. So notice what we just did. By checking just one item, we can eliminate all the items to the left of it or to the right of it just by one query. And this is very useful. And actually, this approach is called binary search. So let's see how this works on our example. So idea is that you divide your search space every time and then devise some results based on the local search space that you're working on currently. So let's see how it works. First, our search space is the entire UCLA store item because we don't know anything about the items initially, only that they're sorted. We check the middle item, middle based on the price of the item. And as you can see here, we actually have an even number of items. And in this case, it doesn't really matter if you choose to check the item for $40 or for $60. Only if you're dividing your storage space roughly by half, that's good enough. So you don't need to worry if this is even, which item do I check? That's not a problem at all. So you decide to check the one for $40 and you realize, and yeah, I can afford it. Well, as we just said in our observation one, we also can afford all the items to the left of it for $2, $10, $23, or including that item, which means that those items to the left of it are not in our interest. They cannot be the most expensive item we can afford because there is an item that's more expensive than them, the book, for example. So we can reduce the search space of the items that we are considering by this range. We only need to check if the book is the most expensive one when, well, it can be if we cannot afford anything to the right of it or anything that's more expensive of it. So now we're only working with the items from $40 to $2,100. Now we decide to check the middle item in that target space. And that is the software for $250. And the cashier tells us that we actually cannot afford it. And this is case number 2 in our observation. This means that we cannot afford items to the right of it. We cannot afford the laptop and for $1,670 and anything that's more expensive than that. So these 3 items are definitely not our target item, definitely not the one we want to buy because we just cannot afford it. So we can eliminate that as well. So notice how we only made 2 checks and we reduced our target space to only 2 items. So we did 2 checks and from 8 items, we got to 2 items. So we reduce our target space by 4, which is understandable because every time we divide our search space by 2, by half. Okay, now we only have 2 items left. And in this case, it doesn't really matter which one is the middle one, they both are. So arbitrarily, you decide to check if the item for $60 is the one that you can afford. And indeed, you can afford that. So here it becomes a little bit, well, not tricky, but you can actually just say, oh, well, I mean, I only have 2 items and I can just handpick whichever one I can use. But for the consistency, we again eliminate all the items in the search space that are cheaper than that, which is the book. So we eliminate the target space, and now the target space is just 1 item. And you double check if you can afford it. Yes, you can afford it. So you pick that item. So to summarize what we just did, we actually on every iteration picked an item in the middle of the search space that we're currently looking at and asked one question: can we afford it or not? Based on the answer to that question, because the list is sorted, we know that we can either afford everything that's to the left of it because we can afford that item, or we cannot afford that item and everything that's to the right of it. So we can reduce our search space either by considering only items to the left of it or consider items to the right of it. So to put it all in the pseudocode, so we repeat the following steps until the search space is 0. First thing we do, we calculate the middle point of the current search space. And initially, our search space is all the items we have. So we calculate the middle point. And, well, if the middle point is something that you're looking for, we stop. In some problems, you can actually tell if that's something you're looking for. Otherwise, if what you're looking for is less than what's in the middle, you can change the endpoint to be just less than the middle point. Otherwise, if you're looking for something that's greater than what's in the middle, you can change your search space to be starting from that point just greater than the middle point. And I want to emphasize that this is not the strict rules that you should follow every time, because as you might have noticed in our example, we actually reduced our search space. So here, when we can afford the item, we actually include that item in our next search space instead of only looking at the items to the right of it. So it's really implementation dependent, and depending on your actual problem statement, if you want to include that item or not, if you're checking less than or equal, greater than or equal, and if you can actually tell if the middle point is what you're looking for. Because in our case, we cannot just by looking at the item tell if that's the most expensive one, if there are more than one item. Meaning that we only have these 2 cases in our case set. So does anyone have any questions about this small pseudocode? Okay, then can someone tell me what the time complexity of this algorithm will be? Sorry? 2n? Oh, like log base 2. Oh, yes, correct. So basically, the runtime of this algorithm, as you just said, is log of n. And actually, in mathematics, usually notation log n means log base 10. But as we talked about in our previous workshops, the base of the logarithm only gives you the constant factor after all. So basically, in algorithmic field and in problem solving, when we say log n, we usually mean log base 2. However, it doesn't really matter for the overall runtime complexity. And this is really good. So every time you make one iteration, you reduce your space by half. And you don't even need to look at all the elements to choose the one that you're looking for. So again, does anyone have any questions? Yes.
So this search is only useful for items that are already sorted.
Yes. So if you're given the items that are already sorted, then yeah, you can use it. If items are not sorted, unfortunately, you cannot apply this algorithm. Because we heavily depend on the fact that, as we said, if we can afford this item, it means everything to the left is cheaper than that, everything to the right is more expensive than that. And in general case, everything to the left is less than that, everything to the right is greater than that. So we can actually reduce the search space. If we don't know this dependence, we cannot say that. Okay, if there are no questions, I'll hand it to Jason for some example problems.
Okay, so we're going to talk about when and where you can use binary search and where you shouldn't use it. So for example, let's say you're given the problem, tell me a time and I'll tell you if I've run a mile faster than that time. And it's definitely faster than 20 minutes. So your job is to find out my fastest mile time. So could you use binary search in this scenario? So yes or no? The answer would be yes, because if you ask me if I can run a mile faster than 10 minutes and I say I can't, then you know for a fact that the search space has to be from 10 minutes to 1959. On the other hand, if I say I can run a mile faster than 10 minutes, then I can also run a mile faster than 10:01, 10:02, 10:03, etc. And so therefore you can reduce your search space to 1 second to 9:59. And so doing this, you can reduce the search space by half every time. And so that's essentially binary search. Okay, so on this next problem, you tell me any day and I'll tell you the number of Academy Awards Leonardo DiCaprio has on that day. So find the first day DiCaprio won his first award. So does anyone have any ideas on how to approach this? Any suggestions? So the approach here would be to use binary search, because let's say we ask if he has any awards today, or I guess some arbitrary day in the past, then he'll have 0 awards every day before today if he has 0 awards today. On the other hand, if he has at least 1 award today, then you know that he won his first award someday before. Then you know that he has 1 award every day after today. So you know he won his first award someday before today. And so therefore you can reduce your search space to every day before today. So on this last example, we're given an integer array A of size n and a target number t, and your goal is to find if t is an A. And so as someone pointed out earlier, you can only use binary search if the array is sorted. So remember to sort your array before you apply binary search. So for example, if you query the kth element and you know it's less than your target, then you know that everything to the left of that is also less than your target. And so you would reduce your search space to the second half of the array. And on the other hand, if you know that it's greater than your target, then you know that everything to the right of it is also greater than the target. So you reduce your search space to the first half. And so on this last question, let's say you want to find the minimum number of coins needed to make a sum of 73 cents. Does anyone know if we can apply binary search here? Any ideas? From you maybe?
I don't see how we could use binary search for this.
Yeah, so that's right. You can't always apply binary search. Like in this case, there's not really any way to apply it. So the approach here would just be to take the largest coin that's less than or equal to the remaining cents. And so the point here is that while binary search is a very powerful tool, you need to know when and where, like when you can use it and when you can use it. So we'll start with a quick pseudocode example. So in this problem, we're given an array and we're trying to find our target. So our target is 19. When we start, our search space is the entire array. So we have start from 0 and at 14. And so as we showed earlier, the first thing we do is we take a look at the middle element. So the middle element here would be the 7th element. And we know the 7th element is 15, which is less than the target. And so because the 7th element is less than the target, we know the 6th element, the 5th element, etc., are all less than the target. And so therefore we can reduce our search space to the second half. So what we do is we set start equal to 8 and equal to 14. And then now our middle element would be 11. And so we do the same thing. We look at the 11th element, which is 23. It's greater than the target. And so we take the left half. And so if we keep on doing this, we should eventually get our answer. So does everyone follow along with how the code works? Okay, good. So we'll get started with an example. Feel free to open the caddis and then try to solve the problem on your own, and then we'll cover it in a few minutes. Okay, then we'll get started with the solution. So the problem tells us that we're supposed to output a number, and then the system will tell us whether or not the number is lower than or higher than the target. And so then, as we just explained, we could linear search guessing every number from 1 to 1,000, but the problem is that we only have 10 guesses. And so the idea here would be to apply binary search. So if we guess n and we get lower as a response, then we know that anything from n to 1,000 can't be the correct number. Alternatively, if we guess n and we get higher as a response, we know that everything from 0 through n can't be the correct number. And so therefore, as we explained in the first half of our presentation, we can apply binary search to find the correct number. So here's the code. We start with our lowest possible number, which is 1, and the highest, which is 1,000. And so we keep on doing binary search until we find the answer. On each iteration, we'll look at the middle element. So that's low plus high over 2. And then we'll output that number as a guess. And so the system will give us a response. If the response is lower than, then we know that we can set our search space to, we can set the upper bound of our search space to whatever we guessed is 1. On the other hand, if the response was higher, then we can reduce our search space to from our guess plus 1 to our previous high. So does everyone understand how we got to this code? Okay, good. So we'll get started with a slightly harder problem this time. Feel free to try this one out and then see if you can solve it. Cool, so we'll get started. So just an explanation of the problem statement. We're looking for the large number h, such that there are at least h papers with at least h citations. So for example, in our input, if we have 71215, then we know that h equals 2 is a valid answer because there are at least 3 papers with 2 citations. On the other hand, if we check h equals 3, we don't have 3 papers with at least 3 citations. And so the highest h could be is 2. So does that make sense to everyone? On the other hand, if we change the sample input to say 71315, well, now we have 3 papers with at least 3 citations, but we do not have 4 papers with 4 citations. And so now our answer would be 3. So one last example. If this is our input where we have a bunch of pretty big numbers, then we know that our answer would be 4 because all 4 of the papers have 4 citations. But since there are 5 papers, our answer would be 4. So I hope everyone understands the problem statement. So as a starter, does anyone know if we can apply binary search here? Yes. So how can we apply binary search? Well, we could always do our linear search from 0 to n, but that takes too much time. So we know that if there are k papers with at least k citations, then 0 to k minus 1 can't be the h index. And the reason is because we're looking for the largest value of k, right? So it's true that if there are k papers with at least k citations, then k minus 1, k minus 2 are both valid answers, but they're not the largest answer. So we cut our search space from k to infinity. On the other hand, if there aren't k papers with at least k citations, we know that k plus 1 all the way up to n can be the h index. And so does everyone understand why this is true? It's not as obvious as the other statement. So if there aren't k papers with at least k citations, then there aren't k plus 1 papers with at least k citations. And so k plus 1 can't be a valid answer. So I hope that makes sense, everyone. And so therefore, if there aren't k papers with at least k citations, then we can cut our search space into the first half of it. So therefore, we can binary search on the potential H index numbers. So how do we check that there are K papers with at least K citations? Does anyone have an answer or have an idea? So we're checking that there are K papers with at least K citations. Yes. Yeah, so we could do that. We could take our input and then sort it and then keep on going until we find a paper with less than K citations. And so that would be the number of papers with at least K citations. So do you know what the time complexity of that would be?
For this?
Yeah, so for the check. So we're checking each of the numbers, right?
Oh, so it's just, the amount, it's like O and it's a constant with the amount of paper.
Yeah, so our time complexity would be O of n, where n is the input. So we just use a simple loop and then count the number of papers with these K citations. For example, we just iterate through every citation. If it's greater than or equal to K, then we increase our count. And then we just need to check that our count is at least equal to K. So here's our solution code. As always, we input our, we take in our inputs, and then we start with 0, and our highest value is n. So does everyone understand why the highest value is n? And not like infinity? Yeah, so we can only have n papers, right? So our answer can't be any higher than n. And so we apply binary search here. First, we check the middle element, and then if it's greater than or equal to that, we set our lower bound equal to mid, else we set high equal to mid minus 1. So it's essentially the same thing that we showed earlier, just applied to, the only thing that's different is the validation. So in order to check that mid works, we just need to do the previously mentioned check. So does everyone understand this piece of code here? Okay, cool. I think that concludes our problem solving part of the presentation. Does anyone have any questions, comments, or concerns about any of the problems or any of the concepts? Okay. If you want to give us feedback, feel free to fill out the feedback form. And yeah, you'll also get an additional entry to the raffle. So I'll give you all like 2 or 3 minutes to fill that out.
Maybe we'll like tell me because there was a question.
Oh, okay. So apparently there's a question on it, so I'll give you like 6 or 7 minutes maybe.